The uncertainty principle, the quantum secret that changes reality, the quantum mystery that defies logic. What if I told you there's a fundamental law of the universe that sets an unbreakable limit on what we can ever know, not just because of our current technology, but because of the very nature of reality itself? A principle that states, no matter how advanced humanity becomes, no matter how precise our instruments are, there will always be a veil of mystery, a layer of uncertainty that we simply cannot penetrate. At first, this might sound like science fiction, a plot from a futuristic movie about a universe that resists being understood. But it's not fiction at all. This is the undeniable reality of the quantum world, a realm where particles exist in multiple states at once, where waves of probability replace the predictable motion of objects, and where observation itself alters the outcome of experiments. This seemingly magical limitation is known as the uncertainty principle, and it's not just a quirk of quantum mechanics, it's a profound insight that reshapes our understanding of existence. It tells us that the universe, at its core, operates in ways that defy the logic of our everyday experience. The certainty we feel in the physical world, the predictability of a rolling ball, or the orbit of a planet, dissolves when we look closely enough. The uncertainty principle wasn't discovered by accident. It was the result of groundbreaking work by Werner Heisenberg in the 1920s, during a time when physicists were unraveling the mysteries of atoms and discovering the quantum rules that govern the smallest scales of reality. Heisenberg's revelation wasn't just a mathematical observation, it was a revolution. It shattered centuries of assumptions about how the universe works and opened the door to an entirely new way of thinking about reality. Here's what makes it even more fascinating. This principle doesn't only apply to abstract particles we'll never see with our eyes. It applies to the very building blocks of your body, the atoms that make up your brain, the particles of light that allow you to see, and even the electrical signals that power your thoughts. The uncertainty principle reveals that uncertainty isn't just a scientific concept. It's woven into the very fabric of existence. Imagine a universe where the more you try to know, the more elusive the answers become, where particles defy logic and behave as though they know when you're watching, where the act of observing changes the outcome, and the question of what's real no longer has a straightforward answer. This is the world of the uncertainty principle, a world that redefines how we understand reality, our place in the cosmos, and the limits of human knowledge. In this video, we'll take you on a journey through this mysterious quantum realm. We'll break down what the uncertainty principle is, explore the science behind it, and discover why it matters, not just for scientists, but for anyone who's ever wondered about the fundamental nature of existence. And along the way, we'll uncover how this principle reveals a universe far stranger and more wondrous than we ever imagined. Are you ready to step into the uncertainty? Let's dive in. The basics of the uncertainty principle. In 1927, the physicist Werner Heisenberg introduced a concept that forever changed our understanding of reality. Known as the uncertainty principle, this idea has since become a cornerstone of quantum mechanics, the branch of science that governs the behavior of the smallest particles in the universe. But what exactly does it mean, and why is it so profound? At its core, the uncertainty principle tells us this. There are certain pairs of properties, called complementary variables, that we can never know with absolute precision at the same time. The most famous example is position and momentum. If we try to measure a particle's exact position, where it is in space, then its momentum, which describes how fast it's moving and in which direction, becomes uncertain. On the other hand, if we focus on determining its momentum with great precision, we lose the ability to pinpoint its position. To put it another way, imagine trying to track a fast-moving object, like a tiny particle zooming through space. If you use a powerful microscope to zoom in and see exactly where it is, the act of measuring it disrupts its motion. It's as if the very act of observation creates a kind of cosmic blur, making it impossible to know both the particle's position and momentum at the same time with perfect accuracy. Now, you might think, well, that's just a limitation of our tools, right? If we build better instruments, we'll be able to measure both properties more precisely. But here's the revolutionary part of Heisenberg's discovery. This uncertainty isn't caused by our tools. It's a fundamental property of nature. It's built into the very fabric of reality. Even with the most perfect instruments imaginable, this limitation will always exist. It's not about how we measure, it's about the nature of the universe itself. This is because particles in the quantum world don't behave like the solid, predictable objects we're used to in our everyday experience. In classical physics, if you roll a ball across a table, you can measure its exact position, speed, and direction at any moment. The ball exists as a clear, defined object that follows predictable rules. But in the quantum world, particles don't act like tiny versions of these everyday objects. Instead, they behave as waves of probability. This means that at any given moment, a particle doesn't have a single, definite location or momentum. Instead, it has a range of possible positions and momenta, described by what's called a wave function. The wave function is like a map of probabilities. It tells us the likelihood of finding the particle in a certain place or state if we measure it. But until we actually perform the measurement, the particle doesn't choose a single state. It exists in a kind of quantum blur, spread out across all its possible options. Here's an analogy. Imagine you're listening to a beautiful piece of music. The sound waves fill the room, vibrating through the air in all directions. You can hear the music, but you can't pinpoint the exact location of every single note. It's spread out, filling the space. A quantum particle behaves in a similar way, existing as a wave of possibilities until we observe it. When we do measure the particle, when we force it to choose a specific position or momentum, we collapse its wave function, narrowing down its range of possibilities. But this act of narrowing comes at a cost. The more precisely we pin down one property, like position, the more uncertainty we introduce into the other, like momentum. This behavior is a direct consequence of the mathematical relationship between position and momentum, described by Heisenberg's famous inequality equation. This equation tells us that the product of these uncertainties can never be smaller than a specific value. In other words, if we try to make the uncertainty in position very small, the uncertainty in momentum must grow larger to compensate, and vice versa. There's a hard limit to how much we can know, no matter how advanced our technology becomes. To truly grasp the significance of the uncertainty principle, it helps to remember that the quantum world operates on scales unimaginably small, far smaller than the atoms that make up your body. At these scales, the intuitive rules of classical physics break down. The universe doesn't behave like a smooth, predictable machine. Instead, it's governed by probabilities, wave functions, and interactions that defy common sense. This realization forces us to rethink everything we thought we knew about reality. It tells us that certainty is an illusion. Even the smallest particles in the universe exist in a state of fundamental unpredictability. And if reality itself is uncertain at its most basic level, what does that mean for our understanding of the world around us? The uncertainty principle doesn't just describe a limitation of measurement. It reveals something deeper about the nature of existence. It tells us that, at the quantum level, the universe is not a fixed, deterministic system, but a dynamic, probabilistic one. And it's this inherent uncertainty that makes the quantum world so mysterious, so fascinating, and so full of endless possibilities. Let's keep going to understand why this principle matters, how it changes the way we see the universe, and what its real-world implications are. The journey into the quantum realm is only beginning. Why does it happen? To truly understand the uncertainty principle, we need to step into the surreal world of quantum mechanics, a realm where particles defy intuition, exist in multiple states at once, and challenge the very concept of objective reality. At the heart of the uncertainty principle lies a fundamental truth. Particles are not solid, point-like objects in the way we imagine them. Instead, they behave like waves of probability rather than physical ripples in space. This is where our classical intuition breaks down. In the macroscopic world, we're used to objects having definite positions and momenta at all times. But in the quantum world, a particle's position and momentum are inherently uncertain until we measure them. Wave-particle duality, the strange nature of matter. One of the most important discoveries in quantum physics is that particles, like electrons, photons, and even atoms, exhibit wave-particle duality, meaning they can behave both like particles and like waves, depending on how we observe them. Think of a single electron. If we imagine it as a tiny ball, we expect it to be located at a single, definite point in space. But quantum mechanics tells us that an electron is better described by a wave function, a mathematical description that represents all the possible places the electron could be at any given moment. This wave function doesn't just tell us where the particle is. It gives us a probability distribution of where we might find it if we tried to measure it. Before we make a measurement, the particle doesn't exist in a single place. It exists in all the possible places it could be, spread out like a wave. This idea is hard to grasp because in our everyday experience, we don't see objects behaving like this. A basketball doesn't suddenly exist in multiple locations at once. But at the quantum scale, this is exactly what happens. The wave function and the collapse mystery. The wave function is the mathematical representation of a quantum system. It provides all possible outcomes of a measurement, whether it's the position of an electron, the momentum of a photon, or the energy of an atom. But here's where things get bizarre. The wave function is not just a theoretical concept. It's a real, physical entity. When we measure a particle's position, we aren't simply revealing something that was already there. Instead, we force the wave function to collapse, reducing all those possibilities into a single reality. This is why the uncertainty principle happens. Before measurement, an electron exists in a superposition of locations, its wave functions spread out across space. When we measure its position, we force the wave function to collapse into a definite location. But in doing so, we dramatically increase the uncertainty in its momentum, because a sharply defined position means the wave-like nature of the particle must spread out in momentum space. Likewise, if we measure the momentum of the particle very precisely, its position becomes highly uncertain. The wave function extends over a vast region, meaning the particle could be practically anywhere. This isn't just a theoretical quirk, it's a fundamental feature of nature. The mathematics of uncertainty. Heisenberg formulated this principle mathematically as the uncertainty in position, the uncertainty in momentum, Planck's constant, which sets the fundamental scale of quantum effects. This equation tells us that if we try to make position uncertainty very small, then momentum uncertainty must grow large to compensate, and vice versa. It's not just a technical limitation, it's a fundamental law of nature. But why does it happen? The key lies in Fourier transforms, a mathematical principle that relates waves and uncertainty. A sharp spike in position space, meaning the particle is localized to a tiny area, corresponds to a broad spread in momentum space, meaning the momentum is highly uncertain. Conversely, a well-defined momentum corresponds to a broad spread in position, meaning the particle could be anywhere. This deep mathematical connection between position and momentum is built into the wave-like nature of quantum systems. Uncertainty and the nature of reality. The uncertainty principle forces us to rethink the very nature of existence. In the classical world, we assume that objects have well-defined positions and velocities at all times, whether we observe them or not. But in the quantum world, things aren't so simple. Does a particle have a position before we measure it? Does the act of measurement create reality? What does it mean for something to exist if its properties are undefined until observed? This principle reveals that reality isn't as fixed as we once believed. It suggests that uncertainty is not just a limitation of our knowledge. It's woven into the fundamental structure of the universe. It's as if nature is whispering, "You can't have it all. Choose wisely." But the implications go even deeper. If reality at the smallest scales is uncertain, what does that mean for the world we experience? Could uncertainty at the quantum level ripple up into the macroscopic world? Could our very consciousness play a role in shaping reality? These are the questions we'll explore next, as we dive into the implications of the uncertainty principle for our understanding of reality itself. Implications for reality. The uncertainty principle isn't just a limitation on measurement, it's a profound shift in how we understand the very nature of reality. It challenges our classical view of the universe as a predictable, deterministic system, introducing instead a world of probabilities, uncertainties, and strange behaviors that defy common sense. In our everyday, macroscopic world, everything seems clear-cut and measurable. If you toss a baseball, you can predict its trajectory with pinpoint accuracy, as long as you know its initial position and velocity. This is the foundation of classical physics, the rules that govern the motion of objects we can see and touch. Classical physics gave us Newton's laws, explaining the orbits of planets and the mechanics of motion, and for centuries, it painted a picture of a universe that was orderly, deterministic, and fully understandable. But the quantum world, the world of particles like electrons and photons, doesn't follow those rules. In the quantum realm, particles don't behave like tiny billiard balls with definite positions and velocities. Instead, they exist as probability waves with no precise location or motion until they are observed. In other words, the properties of particles are not fixed, they are potentialities. It's only when we measure them that they take on specific values. This raises a question that strikes at the heart of our understanding of reality. What is real? The quantum question of reality. Does a particle exist in a specific location before we measure it, or does it exist in a state of uncertainty, spread out as a wave of possibilities? In classical physics, an object exists independently of whether we observe it. A tree in a forest doesn't need someone to look at it to exist. But in quantum mechanics, observation plays a critical role. The act of measurement collapses the particle's wave function, forcing it to choose a specific state. This leads to some unsettling questions. Does observation create reality? If particles only take on definite properties when measured, does that mean reality depends on our act of observation? Are we participants in shaping the universe, rather than passive observers? Is reality inherently probabilistic? The uncertainty principle tells us that we can never know certain properties with perfect precision. This suggests that, at its core, reality isn't deterministic. It doesn't unfold according to fixed rules. Instead, it operates as a set of probabilities, with outcomes that are fundamentally uncertain until they happen. What are the limits of human knowledge? If we can never know a particle's exact position and momentum simultaneously, does that mean there are things about the universe we can never fully understand? The uncertainty principle places a hard boundary on what is knowable, forcing us to confront the limits of our ability to comprehend reality. The illusion of certainty. What's truly fascinating is how the uncertainty principle shows that much of what we take for granted as real may be an illusion created by scale. At the macroscopic level, everything seems stable and predictable. We live in a world of chairs, tables, cars, and planets, all behaving in ways we can measure and predict with confidence. But zoom in far enough, down to the scale of atoms and subatomic particles, and the rules of the game change completely. What appears solid and unchanging at our scale dissolves into a sea of quantum uncertainty at the microscopic level. Particles pop in and out of existence, exist in multiple states simultaneously, and behave in ways that seem almost magical. This suggests that the stability and predictability of our everyday world is an emergent property. a kind of illusion created by the sheer number of particles interacting together. At its deepest level, reality is not fixed, but fluid, dynamic, and filled with possibilities. The role of the observer. One of the most controversial implications of the uncertainty principle is the role of the observer in shaping reality. In classical physics, observation has no effect on the system being studied. You can watch a planet orbit a star, and your act of observing won't change its motion. But in quantum mechanics, observation is everything. When you measure a particle's position, you collapse its wave function, forcing it to take on a definite location. This act of measurement doesn't just reveal the particle's state, it determines it. Before you measure it, the particle exists in a superposition of possibilities, spread out like a cloud. After you measure it, the cloud collapses, leaving a single outcome. This phenomenon has led some physicists and philosophers to ask, does the universe require observers to exist? Could it be that consciousness itself plays a fundamental role in shaping reality? These are questions that touch on the boundaries between science, philosophy, and even spirituality. Implications for the nature of reality. The uncertainty principle doesn't just change how we think about particles, it changes how we think about the universe as a whole. If uncertainty is built into the fabric of reality, then we must rethink some of our deepest assumptions. Reality is not deterministic. The idea that the universe operates like a clockwork machine, with every event following inevitably from the one before, is no longer valid at the quantum level. Instead, the universe operates probabilistically, with outcomes that cannot be predicted with certainty. Reality is participatory. The act of observing a particle changes its behavior, suggesting that reality is not a fixed, independent entity, but something dynamic and interactive. The observer and the observed are intertwined in a way that defies classical thinking. Reality has limits. The uncertainty principle places a hard limit on what can be known, forcing us to confront the possibility that some aspects of the universe are fundamentally unknowable. A new perspective on reality. The implications of the uncertainty principle extend far beyond physics. They challenge our philosophical assumptions about the nature of existence, the role of consciousness, and the limits of human understanding. If the universe is fundamentally uncertain, then perhaps mystery isn't something to be solved. It's an intrinsic part of reality. This realization can be both unsettling and awe-inspiring. On one hand, it means we will never achieve complete knowledge of the universe. On the other hand, it opens up a world of infinite possibilities. The uncertainty at the heart of the quantum world is what makes the universe dynamic, creative, and full of potential. The uncertainty principle teaches us that certainty is an illusion, and that the true nature of reality lies not in fixed answers, but in the endless exploration of questions. It reminds us that the universe is far stranger and far more wondrous than we can imagine. Real-life applications of the uncertainty principle. The uncertainty principle isn't just a mind-bending idea, it has real-world consequences. 1. Quantum tunneling. Without the uncertainty principle, the phenomenon of quantum tunneling, where particles pass through barriers they shouldn't be able to, wouldn't exist. This is how the sun shines, and how modern technologies like transistors work. 2. Quantum cryptography. The uncertainty principle underpins quantum encryption, making it impossible for hackers to measure or copy quantum keys without detection. 3. Quantum computing. Quantum uncertainty is the foundation of qubits, the building blocks of quantum computers. These devices could revolutionize computing by solving problems that are impossible for classical machines. How it changes our perception of the universe. The uncertainty principle reveals that the universe isn't deterministic, it's probabilistic. At the smallest scales, reality is a blur of possibilities, only becoming definite when observed. This idea leads to one of the most famous questions in quantum mechanics. Does the universe exist independently of observation, or does observation create reality? Some physicists argue that reality is fundamentally shaped by consciousness. Others believe the universe operates on its own terms, with or without us. Either way, the uncertainty principle challenges us to rethink the nature of reality itself. It tells us that certainty is an illusion, and that at its heart, the universe thrives on mystery. Fascinating thought experiments. Let's make this idea even more tangible with a couple of thought experiments. 1. The microscope paradox. Imagine trying to observe an electron using light. To get a clear view, you'd need to use light with very short wavelengths. But shorter wavelengths carry more energy, which disturbs the electron's motion, making its momentum uncertain. It's like trying to measure something while shaking it. 2. The double-slit experiment. This classic quantum experiment shows how particles behave like waves, until we observe them. When not observed, particles pass through both slits, creating an interference pattern. But when observed, they behave like particles and go through one slit. The act of measurement changes the outcome, highlighting the essence of quantum uncertainty. The ultimate mystery. What does the uncertainty principle truly mean? Not just for science, but for us as human beings. What does it reveal about the universe, about knowledge, and about our place within this grand cosmic framework? At its core, Heisenberg's uncertainty principle does more than define the limits of measurement. It tells us something profound about the nature of existence itself. It forces us to confront a reality that is not fixed, predictable, or even fully knowable. It challenges the very foundation of classical thinking, the belief that the world can be precisely understood, mapped, and controlled. This realization may seem unsettling at first. We like to believe that if we ask the right questions, develop the right theories, and refine our instruments enough, we will eventually uncover all the secrets of the universe. We dream of a future where science has answered every mystery, where every phenomenon has been explained. But the uncertainty principle tells us that some mysteries will always remain. And yet, perhaps this is not a limitation, but a gift, the beauty of the unknown. The uncertainty principle reminds us that the universe is far stranger and more intricate than our minds can fully comprehend. It tells us that there are built-in limits to what we can measure, but within those limits lies endless potential. Instead of being a barrier, uncertainty is what allows reality to be dynamic, creative, and ever-evolving. It ensures that the future is not rigidly determined, but filled with infinite possibilities. Consider this. If the world were perfectly predictable, if everything could be known with absolute precision, would there be any room for wonder, for exploration, for discovery? The greatest breakthroughs in history, from Einstein's theories of relativity to quantum mechanics itself, did not emerge from certainty. They arose from the willingness to question, to embrace the unknown, and to explore the edges of what seemed possible. In this way, uncertainty is not something to fear. It is the engine of discovery, the force that drives us to look deeper, think bigger, and question more boldly. Are we part of the cosmic mystery? The uncertainty principle suggests something even more extraordinary. The observer is not separate from the observed. In classical physics, we assume that reality exists independently of us. A planet orbits a star, whether or not we are watching. A rock exists, whether or not anyone perceives it. But in the quantum world, observation is not passive. The very act of measuring a particle's position changes its nature. Before measurement, it exists in a state of probability, a wave of possibilities. After measurement, it takes on a single, definite state. What does this mean for us? Could it be that we are active participants in shaping reality? That the universe is not simply out there, but intertwined with our observation, our consciousness, our choices? Some physicists and philosophers have even suggested that consciousness itself plays a fundamental role in collapsing wave functions, bringing reality into focus from a sea of probabilities. This idea remains deeply debated, but it raises fascinating questions. Does the universe require observers to bring it into being? Are we, in some way, entangled with the fabric of existence itself? Is the act of wondering about the universe part of what creates the universe we experience? The uncertainty principle leaves room for mystery, and in doing so, it opens the door to possibilities beyond what we can currently imagine. A universe that whispers back. Think about the night sky. When you gaze up at the stars, you are seeing light that has travelled for thousands, even millions of years. You are witnessing the past, touching infinity with your eyes. Now imagine that at the deepest levels of reality, even the tiniest particles do not fully exist until they are observed. The universe is not a static thing, unfolding like a machine. It is alive with probabilities, waves of potential that respond to interaction, to observation, to participation. It's as if the universe is whispering, "You can never know everything," but in the act of seeking, you become part of the very thing you are trying to understand. Embracing the infinite. The uncertainty principle teaches us to let go of the need for absolute certainty. It invites us to explore, to wonder, to accept that some mysteries will never be fully solved, and that this is precisely what makes life meaningful. So, the next time you look at the stars, remember this. The same quantum uncertainties that shape the tiniest particles also shape the universe itself. You are not separate from this mystery. You are part of it. Even the smallest particle holds secrets we are only beginning to uncover. And in those secrets, in that uncertainty, lies the true wonder of existence. The uncertainty principle isn't just a rule of quantum mechanics. It's a doorway into a deeper understanding of reality. It challenges us, inspires us, and reminds us that the quest for knowledge is endless. What do you think? Is the universe fundamentally uncertain, or is there a deeper truth waiting to be discovered? Share your thoughts in the comments, and don't forget to subscribe for more explorations into the mysteries of the cosmos. Together, let's keep questioning, imagining, and reaching for the stars.